All right, 5.3, electric cells. This is the only equation we have for the data booklet. Epsilon is equal to I times R plus little r. This epsilon is the voltage of a battery, as always. I is the current through the circuit. Big R is the resistance of a load, like an external resistor, a diode, and little r is the internal resistance of the battery itself. So we will be calculating internal resistance for various cells. The first type of battery is the acid battery. It contains an acid, which is an electrolyte, and two electrodes made of different metals. Different metals dissolve in acids at different rates. They have different reduction potentials. And when a metal dissolves, it enters the acid as a positive ion, leaving behind an electron. So acid, two different types of electrodes. The cations are supplied by the acid. Electrons come from the metals. The least negative metal is the positive terminal. The most negative metal is the negative terminal. Think of a chemical cell as a device that converts chemical energy into electrical energy. We will be drawing energy diagrams and analyzing them in topic 8. So these electrons that are pushed around the circuit can be used to illuminate light bulbs and essentially do work for us. So the question is, why do the electrons run from negative to positive in the external circuit instead of protons running from positive to negative? It's a good question. Each time an electron leaves the negative terminal, the acid then creates another electron. Each time an electron enters the positive terminal, the acid neutralizes an electron. The process is maintained until one of the metals or the electrolyte is completely used up. A primary cell cannot be recharged, so that includes your typical alkaline batteries you buy at the store. It has a paste inside of it with a conductive rod, and once that paste is used up, you can't recharge that battery. You have to take it apart. It's useless. Secondary cells can be recharged, like your car batteries, by applying an external voltage, such as lithium ion. That's what you do when you recharge your phone, your laptop, and whatever else includes a rechargeable battery. You can reverse a chemical reaction. So in lead acid batteries, you can recharge it by adding more sulfuric acid to the battery. Okay, back in the days of Benjamin Franklin, scientists understood that there were two types of electricity, positive and negative. Really, it was Benjamin Franklin's idea to name it like that because he did work in finance, and in finance you have debit, where you can have positive account, and credit, where you have a negative account. And he related the electrical phenomena with money. But what Benjamin Franklin didn't know was whether or not the positive or the negative type of electricity was moving. And so because positive money, moves around the world, he thought that it was the positive charges. He had a 50-50 chance of getting it right, but he was wrong. That's okay. It really doesn't matter. So in truth, the cell, the ions move, or the electrons are the ones that move around the cell, but as we will see, the convention that we have shows the opposite. So in this class, indeed, all around the world, people still use this conventional current, this idea that it is the positive charges that move around. So on the right-hand side, you can see how the cell actually behaves. The left-hand side was the conventional current, how cells were originally thought to behave. This is conventional current. It's still used in circuit analysis. Not really sure why it hasn't changed. It probably won't ever change. Okay, so remember from topic 5.1, the electric potential difference, delta V, is the amount of work done in moving a positive charge Q from a point of lower potential energy to a point of higher potential energy. It takes work to move charges around a cell, or to move charges around a circuit. So the units for electric potential difference are volts, and that can be seen from the formula joules per coulomb. And electric potential difference is often abbreviated PD. So it's good to think of a battery like an engine. This engine uses chemical energy to move these positive charges to a high potential within itself, within the cell itself. Then it drives those positive charges out to the external circuit to do work. Analogous to gravitational potential energy, think of a battery as an elevator driving up charges to a high potential. Here we go. Here's our conventional current positive charge going around the circuit. As the charge travels around the circuit, it is reduced to a lower potential energy. So the battery, the chemical cell, drives up the positive charge. These spinning wheels represent resistors, diodes, light bulbs, anything that uses up that energy and allows the charge to travel back to the chemical cell, completing the circuit. Okay, the electromotive force, or EMF, of a cell is the amount of chemical energy converted to electrical energy per unit charge in moving charges from one terminal of the battery throughout the circuit to the other terminal. Energy per charge is volts. EMF is measured in volts. And just because it says force, it's not actually a force. That's just what Faraday thought it was. But voltage is energy per charge. Not quite a force. Okay, you can measure the potential difference across the terminals of the battery, and when you do this without any type of component attached to the battery, without any external resistor, we say that this is an unloaded circuit, so you get a certain value for the voltage in this setup. Okay, so if we connect a resistor as part of an external circuit to the cell, we can see that the voltage read by the meter goes down a little bit, and we say that this cell is loaded because there is actually an external resistor connected to it. So all cells, batteries, are limited in how quickly they can convert. They can use these chemical reactions to maintain the voltage. There is internal resistance, lowercase r, associated with a cell or a battery, which causes the cell's voltage to drop when there is an external demand for the cell's electrical energy. Best cells, really well-made batteries, will have very small internal resistances, and the internal resistance of a cell is why a battery becomes really hot if there's high demand for current from an external circuit. There are no free highways in a battery either. I mean, these electrons are having to move through materials, and as they move, things can get hot. So cell heat will be produced at the rate given by this equation. Power equals I squared times lowercase r. So this is just like any of the power equations you have, just lowercase r, instead of representing external resistance, is the cell's internal resistance. So you know you're dealing with a problem that involves calculating internal resistance when you see a schematic that looks like this on the right-hand side. There is a cell and a resistor right next to each other, and they're typically enclosed in like a box. Not a blue box usually, but this is your clue, like, okay, I'm going to have to use this equation, or I'm going to have to analyze the internal resistance of a battery. It will typically be connected to a single resistor because without a load, you can't ascertain what is the internal resistance of the cell itself. Okay, quick derivation of the equation. From potential energy equals Q times V, this is work is equal to Q times voltage. We can deduce that electrical energy being created by the cell is E sub P equals Q times epsilon, where epsilon is the voltage of the cell. The electrical energy being converted to heat energy by an external resistance R is Q times the voltage dropped across that resistor. The electrical energy converted to heat by the internal resistance then is Q times the voltage lost across the internal resistor in the cell. Conservation of energy tells me that E sub P equals the potential energy dissipated, or the electrical energy dissipated by the resistor plus the electrical energy dissipated within the cell. So we can replace that with our Q equations. Charge times epsilon equals charge times the voltage across external R plus charge times the voltage within the battery, and the Q's cancel. It's the same amount of current flowing through because, yeah, current is the same everywhere in series, and from Ohm's law, V is equal to I times R, so that is how we obtain this relationship, epsilon equals IR plus I lowercase r, you can factor out the I, and you can also replace I times capital R with V, because that's the voltage dropped across that particular component in the cell, in the circuit. Okay, first question. This is about internal resistance of a cell. Define EMF. Make sure you use words like energy per charge. IB has so many questions over the years on defining EMF, energy per charge, and include things like charges moving around the cell, moving around a circuit, circuit from one terminal to the other. So put this into nice, like 1 or 2 sentences. Okay. Part B, a circuit is used to determine the internal resistance and EMF of a cell. It consists of the cell, a variable resistor, an ideal ammeter, and an ideal voltmeter. The diagram shows part of the circuit with the ammeter and voltmeter missing. Draw on the diagram the positions of the ammeter and the voltmeter. So this is easy. All you have to do is know you are measuring the voltage of the cell. You're trying to determine the internal resistance and EMF of a cell. So you want to connect the voltmeter to the variable resistor, and you want to make sure that you correctly connect the ammeter in series with everything. So remember, voltmeters are wired in parallel, ammeters are in series. 1C, the variable resistor is set to 1.5 ohms. When the cell converts 7.2 millijoules of energy, 5.8 millicoulombs of charge moves completely around the cell. The potential difference across the variable resistor is 0.55 volts. Show that the EMF of the cell is 1.25 volts. So to do that, we know that it's the EMF that causes these charges to move, and it takes this amount of energy to do it, the 7.2 millijoules. So we can use this equation, V equals work over Q, and this V is our epsilon. All right, part D, we're getting the internal resistance of the cell, so we'll use this equation. Epsilon is equal to I times the resistance of the resistor plus our unknown internal resistance. To get I, we need to use the information given about the resistor itself. V is equal to I times R. So the voltage across the resistor divided by the value for the resistor gives me I. So 0.55 volts dissipated divided by 1.5 gives me current. I'll plug this in for right here. I know what epsilon is because we just solved for it. All that's left to do is to isolate the lowercase r. Practice 2. A battery of internal resistance 2 ohms is connected to an external resistance of 10 ohms. The current is 0.5 amps. What is the EMF of the cell? Easy. Epsilon is equal to I times big R plus little r. Question number 3. A battery of EMF epsilon and negligible internal resistance is connected in series to 2 resistors. The current in the circuit is I. State an equation giving the total power delivered by the battery. This is easy. Power equals current times voltage, and in this case, the voltage of the battery is labeled epsilon. The potential difference across resistor R1 is V1, and that across resistor R2 is V2. Using the law of conservation of energy, deduce the equation epsilon equals the sum of the voltages V1 and V2. Well, I know that voltage is equal to work, energy per charge, so voltage has to be, work has to be voltage times charge. All of these components are in a line, which means they all get the same amount of charge at any given point, or at any given moment in time. So this is energy conservation. Epsilon times Q equals V1 times Q plus V2 times Q, and then I cancel the Q's, and then I've arrived at my target. It's that easy. The graph shows the current voltage characteristics of 2 conductors, X and Y. On the axes, sketch graphs to show the variation with the potential difference V of the resistance of conductor X, you'll label that line graph X, or you'll label this graph X, and the conductor Y, label that line graph Y. You do not need to put any numbers on the vertical axis. That makes it nice. Okay, so you're going to be sketching a graph on the provided axes of resistance versus voltage. So let's look at what's going on, and remember, resistance is equal to voltage over current. So we can get a sense of what these graphs should look like. First thing, the X graph seems pretty easy. It's totally linear, which means that it has a constant resistance. So this is X is an ohmic resistor. This is an ohmic circuit. Now for Y, things are a little different, because in the Y graph, we have the current much, much higher initially than the X graph. So this means that if the current is just really, really high, then initially Y has a lower resistance. In fact, because the current stays high for so long, it has a lower resistance all throughout until it starts to, and it's gradually increasing until the two have the same resistance at 4 volts. So the two graphs, the graphs that you draw, will intersect at 4 volts, and then it seems that the resistance for I just gradually continues to increase. So for the X graph, this is what I would say. X is constant, and it must have a higher resistance than Y for most of the graph, for most of the voltage. So up to 4 volts, graph X is like this. And then up here would be 4 volts. Okay. Graph Y, on the other hand, the resistance is changing, and the resistance is less than graph Y. And why is that? Yeah, because the current is higher, and the more current, the less resistance. So I will have like this curve coming up, and then around 4 volts, the two intersect. And this is my graph Y. Okay, part D, the conductors in C are connected in series to a battery of EMF epsilon and negligible internal resistance. The power dissipated in each of the two resistors is the same. Using the graph given in C, determine the EMF of the battery and calculate the total power dissipated in the circuit. So the power dissipated in each of the resistors is the same when the two graphs intersect. So right here. And they have, at this position, not only is the voltage dropped across them the same, but the current is the same. That means the power across them is the same. So power equals I times V. If these two are in series and both of them experience a voltage drop of 4, voltage sums in series, so that means the EMF of the cell has to be 8 volts. And that means that the total power dissipated in the circuit is the sum of the power dissipated across X and across Y. So you can finish this one up. A resistor of resistance 1.5 ohms is made from copper wire of radius 0.18 millimeters. The resistivity of copper is 1.7 times 10 to the minus 8 ohm meters. Determine the length of copper used to make the resistor. This one is easy. It's from topic 5.2. The manufacturer of the resistor in A guarantees that the resistance is within 10% of 1.5 ohms, provided that the power dissipation in the resistor does not exceed 1 watt. Suggest why the resistance of the resistor might be greater than 1.65 ohms if the power dissipation in the resistor is greater than 1 watt. Okay, so more power dissipated through, higher the power, more heat. Which means that the temperature goes up this can change the resistance. Hence, the manufacturer has specifications. It's 1.5 ohms if you're within 1 watt of power. Okay, show that for a power dissipation of 1 watt, the current in the resistor of resistance 1.5 ohms is 8.2 amps. I wonder what power equation you can use to solve for current. Finally, part D, the 1.5 ohm resistor is connected in series with a variable resistor and a battery of EMF 6 volts and internal resistance of 1.8 ohms. Estimate the resistance R of the variable resistor that will limit the current to 0.82 amps. So we can use Old Faithful here. Epsilon is equal to I times R, and it could be R1, plus R2, plus little r. It doesn't matter, these are all in series, so it's just the total resistance in series. Choose one of these R, capital R's, to be your target variable resistor. You have the current 0.82, 6 volts, you know your internal resistance, it's a cakewalk.